Alright, hi everyone, this is Alfred from Nerd of Passion, and welcome to the second live stream lecture. I'm really sorry about the earlier, there was some problem with the audio and I didn't realize it until halfway through, and then my girlfriend let me know that there was no phone, the microphone wasn't working. So for those of you who watched it just now and realized there was no audio, I'm really sorry, and I will make sure that will not happen again in the future. For today's lecture, I will be talking about revolutionizing physics and the breakdown of classical physics. Okay, so for today's lecture, I'll focus more on the bigger picture. So just to give you guys like a better understanding, like what exactly is modern physics and like what are all the files about this all about, and and how classical physics breaks down at the microscopic level. And once again, so for those of you guys who are watching this, I just want to say a big thank you, and I really appreciate you guys for coming here. It really means a lot to me. So just let me get started. So I'll just fire up my PowerPoint slides, just get my recording software up and running. Right, so to put myself down here in a corner. Yep, nice and small, and the screen nice and big. Yep, right here, and just go all the way up. Okay, so it's over here. And before we get started, I'll just put on my nerdy glasses. And also for this lecture, I highly recommend you downloading the lecture handout. The link is provided down in the video description. You can get the lecture handout down from my website. Right. Okay. So let me get started. Okay, so I'll start off at the bigger picture and looking at like what is modern physics. Okay, so modern physics basically refers to the physics that is developed at the start of the 20th century, and I would say at the start of the 20th century is truly a remarkable time for physics, because during that time there were many like groundbreaking ideas. There were like a lot of like discovery that really changed the way scientists look at the universe all around us. Okay, so what about classical physics? So like like the old physics. Does that mean they are wrong? Actually no. They are accurate in the macroscopic world, like the world we live in every day. But in the microscopic world, we really need a new form of physics to describe what is going on. I'll get into that a bit more later. So classical physics usually involve things like like the very familiar physics around us, like mechanics, like the motion, like Newton's law, kinetic energy, momentum, so on and so forth. Thermodynamics, like the study of the flow of heat, and like electromagnetism, electric charges, magnets, and so on. And modern physics, I mean, there is so much stuff going on in modern physics, and in today's lecture, I'm just going to scratch on the surface on what is going on in modern physics. So the two big pillars of modern physics is, first of all, quantum physics. I don't really have any like nice picture to show you because it's down in microscopic level. It's kind of hard to like draw pictures of what is going there or on there. So this is like just a nicer picture to show like some calculations involved in quantum physics. And so to summarize it in like one sentence, like what quantum physics is all about is particle and waves, they are all unified as one single entity. And of course, I'm not really doing quantum physics enough justice by summarizing one sentence, because there's like so much going on in quantum physics and so much weird stuff going on. But this little sentence just allows us to catch a glimpse of what quantum physics is about. And so some technological innovations and like development is possible because of quantum physics is of course semiconductors. And so semiconductors, they are the basis of modern electronics and the computers. So the phone, iPhones, and everything we use today is all possible because of semiconductors, and that ultimately led to the development of integrated circuit chips and like really tiny processors and so on. And of course lasers, they are very fun to play with. And spectroscopy. Okay, so spectroscopy, I mean it has been around for a long time already, but the thing is back then nobody knew like why it was the case. So for those of you who have no idea what spectroscopy is basically the study of how do you identify like molecules or like atoms by studying like the colors of light that it gives off when you heat it up. So that is a kind of basic idea behind spectroscopy. For those doing chemistry, you study spectroscopy in a little bit more detail. The other big pillar of modern physics is of course relativity. Relativity is a very famous theory developed by Albert Einstein. Actually, relativity is the theory that made him like really famous. So till today, we remember him as one of the greatest physicists of all time. I mean, whenever I see Einstein name like in physics books, like, oh yeah, that guy, right? So relativity, to summarize it in one sentence, it's is this. Light travels at a constant speed of 300 million meters per second. That roughly translates to 300,000 kilometers per second, no matter where you look at light. So you can be standing still, you measure speed of light, you're going to measure that speed. If you move along with the light and you measure the speed, you also get the exact same speed. If you move in the opposite direction, you expect light to move faster, but nope, it still moves at that speed. And the constancy of speed of light has really like disturbing consequences. Things like like when you move fast, time starts to slow down, and then like length start to contract, and things like that. Okay, so some technology that is possible with relativity is nuclear technology. Like nuclear weapons, nuclear power, so on and so forth. And so all that is possible because of relativity. Also is also more involved in quantum physics as well. The famous equation E is equal to mc squared. So that comes from relativity. And of course, it is also used in like GPS. So GPS, the reason is because down here on the surface of the Earth, times flow a little bit slower than the GPS satellite. So we need relativity to correct for that. And of course, relativity also predict like weird things like curvature of space-time. So say you have like a planet, so what happens is the space-time around it is curved, so when it shines light, it bends the light. So that forms the basis of like modern astrophysics. And so these two like a fundamental like areas in physics ultimately led to the development of many other areas in modern physics. So I think in the lecture handout I've put a few examples there. So in things like quantum field theory, particle physics, condensed matter physics, astrophysics, and so on, and also atomic physics. There's like many like exciting new development that even till today is still a very active area of research. So even today we are still finding out a lot more things with going on in the modern physics. Right. Okay. So what about for year 12? So you might be wondering. So which one are we going to look at? So in the year 12, we are going to look at the interaction between a light and a matter, and of course that is quantum physics. So the physics of the microscopic world. So it's one of the most fascinating areas in physics, and of course one of the most challenging one, because in order to really get down to it, you need to learn a lot of math. So you need to spend like a few years learning how to solve like differential equations, advanced calculus, so on and so forth. And then you need to learn how to do like algebra, like linear algebra, and then with that, and then you start to learn quantum physics. So this is just a picture, like some typical calculations involved in quantum physics. And also it predicts a lot of weird things. Things like the Schrodinger's cat. The cat being dead and alive at the same time. And of course, quantum physics is also my area of specialty. I pretty much do quantum mechanics every day. At the moment, I'm more focused on applications of quantum mechanics. Like applying all the principles into more realistic systems. I think I've talked a bit about this in my previous lecture. And so this picture is like some simple calculation of me, working on the stuff in quantum physics. Okay, so what quantum physics really study is that we will really examine the deep nature between light and matter, and of course, how they all interact with one another. And what we find is that there is a very puzzling surprise that awaits us when we really dig deep and try to figure out what is going on at the microscopic, in the microscopic world. Okay, so I think the best way to begin, by understanding how groundbreaking quantum physics is by first of all let's have a look at the atomic structure, since we are going to look at very tiny things. And so if you look at the atomic structure, so if you guys recall from the structure of the atom, so what do we have? So here's a very nice picture of an atom. So it's a very simple. So what do we have? We have a nucleus that consists of protons and neutrons that all lumping together, forming a nucleus, and it's really dense. And of course we have electrons orbiting around the atom. And not only that, if you're familiar from chemistry, so the electrons are only allowed to orbit at certain levels. So from chemistry you learn like the first shell, so like helium has 2 in the first shell, and then next is lithium, so 2 in the first shell, 1 in the second shell, and so on. So this means that electron, they can only be orbiting around the atom at a fixed level, and that fixed level in chemistry we call it electronic configuration. Okay, so I mean it's a very simple model, but the thing is it also presents many problems if you actually think about the model properly in terms of classical physics. Okay, so some serious problems with the atomic structure. Okay, so the first one is this. Okay, so when I first studied the atomic model, this is the first problem I was really wondering about, and it troubled me for quite a long time until I figured this out when I look at nuclear physics. So in the nucleus, we have the protons and the neutrons all lumped in together. Okay, but the thing is, each protons, they are positively charges, and because they are positively charges, they should be repelling each other. There is no way they can all lump in together. Okay, so this actually the answer to this question, I will not be covering that here. It's actually answered in the nuclear physics, and it's pretty much like there is another force that is holding them together, which is called the strong nuclear force. And next, okay, so when the electrons, they are orbiting around the atom, okay, so what happens is they are oscillating. So if they go up, down, up, down, up, down. Okay, so if you kind of study electromagnetism a bit further, you'll find that if a charge is oscillating, actually in reality what is happening is it's actually starting to radiate energy. Actually that forms the basis of like a telecommunication. So with an antenna, and then in there, the charges, we let it oscillate, and then when they oscillate, they send off an electromagnetic wave. And when they send off electromagnetic wave, they carry off energy with them. Okay, so what this means is that the electron shouldn't be able to orbit the nucleus at all, because what happens is when it orbits, it loses energy, and then when it starts to lose energy, the electron will immediately collapse right into the nucleus. And then if you run like some classical calculations, you find that this structure is unstable. I think it collapses like in like nanoseconds. It's like you have the atom, immediately the electrons collapse right into the nucleus. So of course something is very wrong, like because atoms, as we know today, they do exist. Right, and of course the next question is, okay, so what about the electrons? Like, how do they know where to orbit in the first place? Like what is the thing, making sure that they orbit at the first level, the first shell, second shell, third shell, and so on. Yeah, and so it seems like the electron already like know where to orbit by itself. So that is a really weird aspect as well. And okay, so for this lecture, this is the question that I hope that I'll be answering by the end of the lecture, which is this. So why does the heated gas atom, so you have a gas consists of an atom, and when you heat them up, you only produce wavelengths of light at a discrete level. So which means you only get certain colors of light. This is also actually the reason why different things around us have different color, because they have a tendency to produce different wavelengths of light. Okay, so this is like a little experimental setup that measures like this, we call it the electromagnetic spectrum. So we have the gas, we heat it up, and then when it produces light, we pass it through a slit to ensure that they all move in one single direction, and then we put it through a prism which spreads the light into the different wavelength or the different colors. And so what we find is that if we use gas, this is what we see. So for hydrogen, you see it produces like quite a lot of like the violet light, and then one in the red light. And then for helium, it produces its own unique set of spectrum as well. Same thing for neon, sodium, and mercury, as a picture I've attached on the right. Okay, so if you look at this, I mean, it's really weird. Why light is actually produced at this certain level, and each atom has its own signature wavelengths of light, or its own signature color. And so this forms the basis for spectroscopy. So by studying like the type of light that is produced by the gas, we can actually figure out like what the element is, without actually having to get it to react with something. Right. Okay, so confounded with this new problem, so what physicists find is that classical physics, it feels really bad if we try to put it down in the microscopic level. So as you know, like the serious problems that I've presented in the previous slides. Okay, so the picture, like the little comic I've put up there, pretty much summarizes how physicists feel back in the day when they were like, kind of like trying to figure this out. Right. Okay. So so it seems like if you're going to look at the microscopic world, like in the tiny world of atoms, we need a new form of physics, like a total change in the worldview to try to figure this out. Okay. So from there, so you know, like physics, they kind of sat down, they really worked it out. Okay. It all started in roughly in the 1900s, and which is actually, when you think about it, it's really impressive, because that is just like about 120 years ago. I mean, even less than that. And that ultimately led to the development of quantum mechanics, which today, you know, during that time we call it the quantum revolution. And okay, so before we get to the answers, you know, that I've posed on the previous slide. Okay, so first of all, we need to like ask ourselves, you know, like the nature of light. Because by studying the nature of light, we'll be able to find the crucial piece of puzzle needed to answer the question, how does spectroscopy really work? Like, why does gas produce discrete wavelengths of light? Okay, so now let's take a minute and think about like what is light. Okay, so I mean, light is all around us, but the thing is, the nature is like it's mystical. It's like really weird. I remember when I was a kid, I'm always troubled with the nature of light. Like, because light, you know, it always seems to, like, the moment you turn on a light bulb, it fills up the space like immediately. We can't really touch light. I mean, you can't have a light beam and then you go grab the light. Like, because you can't really grab the light, and then when you shine the light beam on your hand, you don't really feel the light at all. So it seems like not really like a physical entity. And but the thing is, actually it does. Technically, you can feel light. Like, if the light is strong enough, you can feel it as a heat. So it definitely, you know, involves like some sort of energy transfer process. And so here are just some nice pictures to kind of think about the nature of light. So on the left, you see like a nice, you know, they cast shadows. You know, light bulb. You know, we need electricity to produce the light. And the picture on the right is a nice picture of a sunset. You know, it's like if you go to sunset and it happens to be cloudy, you see like a very beautiful light rays of forming. Okay, so the nature of light. Okay, so it's a really like mysterious. But can physics really answer the question? Okay, so if you're like thinking about this, good for you, because this has been really thought about like few hundred years ago, like during Newton's time. Okay, so let's kind of look at slightly different thing, like a slightly different thing in the physics. Okay, so classically, you know, like in physics. Okay, so every energy transfer process. I'll show you how this is linked to light later. Okay, so every energy transfer process around us can be definitely involve either particle collision or wave energy transference. Okay, so what is going on over here is that particle collision is when one particle, you know, bump into another particle, and you know, it transmits the energy. But for wave, okay, so imagine two balls resting, like floating on the surface of water. If one starts to shake up and down, what happens is it disturbs the water surface, and you know, that sends off a wave, and then this ball, you know, starts shaking up and down as well. So it's kind of like you're transmitting energy from this ball to the other ball. Okay, so these are two mechanisms behind like pretty much every energy transference all around us. Even things that don't really seem to appear, appear as these two things, actually can be explained by them. Say sound. Okay, so sound, it can be explained by sound waves. So you know, when I talk, I'm actually vibrating. My vocal cords are vibrating, and that vibrates the air molecule around us, and then that spreads out as a sound wave. Okay, so for say heat conduction, you know, heat flows from a hot place to a cold place. So that can be explained by particle collision. So when an object is hot, the particles in there are vibrating a lot faster. So when it comes in contact with a cold object, so what happens is the faster vibrating molecules kind of heat all the molecules that are vibrating slower. So what happens is they transfer the energy in that process. So that is a particle collision energy transference. Okay, so now since the light transmits energy, it must be either a wave or a particle. I mean, that obviously, because it transfers energy. So, but the question is, which one is it? Okay, so I think I'll start off by giving you the answer like right away, and then I'll show you like the timeline of discovery. So as time goes along, you know, how scientists slowly figured all this out. Okay, so what we know now is light is both a wave and a particle. Okay, so this is the one little discovery that really changed everything in physics, and it was a really mind-blowing discovery back then. So when scientists was like, oh wait a minute, a light is both wave and a particle. Like what? Like how is that even possible? But that is like how a light really is. So these little particles, we call them photons, and you know, when they travel, you know, they travel like a particle, and they have like a little wave attached to it. So that little picture I've drawn over there, like kind of like illustrates how light, you know, kind of works. And of course, like there are like different models possible as well. So it's like a little like wave packets. So you know, when light travels, it kind of creates like a wave, and all the waves, they are kind of like behave like a little a particle. And these like particles, we call them photons. You know, like light particles. Okay, so photons, when they travel like as packs, so which means you get like a whole bunch of photons, and you get them to travel together. And so they manifest themselves as electromagnetic waves. So which means when you try to like study them, when you look at them, say, oh yeah, it's a wave traveling. But actually, when you kind of look at from a closer perspective, what you find is that, oh, you know what, they consist of like little particles. It's almost like saying, say you have a ball and then you roll it down the street. So when you roll down the street, and then it becomes a wave, and then when you grab the ball on the other hand, it becomes back a ball. So it's kind of like, so it's not really clear, like, you know, like how can we like picture a wave and a particle both at the same time. And so this actually what makes quantum mechanics like one of the more difficult theories, is because you can't really visualize what is going on, but we do know the answers, because it kind of goes against our everyday experience. Right, okay, so to give you a bit more context of like how all these ideas have come along, I'll just give you like a little timeline of discovery. Okay, so roughly in the 1700s, okay, so that is during the time, you know, Newton like proposed his like theory of mechanics, you know, Newton's law, F equal to ma, so on and so forth. Okay, so during that time, so Newton, he proposed his theory on light. But the thing is, during that time, he has a rival. His name is Christian Huygens. He proposes a wave model of light. Okay, but the thing is, they both have very compelling reason why light is a particle, and why light is a form of wave. Okay, but the problem is, but the thing is, nobody knew, because there was no like experimental evidence to support either one of them. Because when the wave nature and the particle nature is very, very, very difficult to detect. You need like very extreme conditions, which back in the days is very difficult to like get those like conditions and get those equipments. Okay, so but the thing is, when Newton proposed this idea, majority of the scientists actually believe in Newton, because first of all, it makes a lot more sense. Oh yeah, it's like particles. It's like a lot easier to work with compared to the wave theory. Okay, but the thing is, 100 years later, okay, so this guy named Thomas Young, okay, so he demonstrated that, you know what, based on the double slit experiment, you know, light actually behaves as a form of a wave. Okay, but the thing is, when Thomas Young he did this experiment, many scientists were still really reluctant to believe that light is indeed a wave, which until like roughly 60 years later, so in the 1860s. So this very famous scientist called James Clerk Maxwell, so he used the laws of electromagnetism to really show that light is actually a form of an electromagnetic wave. So what is an electromagnetic wave? Actually, I've kind of explained that a little bit more detailed in the lecture handout. I don't think I have time to kind of go through that with you. So what it is just oscillation of electric and magnetic fields. So like between 1800s to 1860s, so during that time, so Maxwell showed that light is a wave, so that pretty much convinced everyone that, oh hey, you know what, we've kind of solved a very big puzzle in physics. Yeah, we can celebrate now. We found out that light is actually a form of electromagnetic wave. Okay, but there was a few problems in physics that the wave model can't really predict properly, and that brings us to the time where the quantum revolution was actually starting to happen. So roughly at the 1900s. So during that time, there was something called a photoelectric effect that the wave model can't really explain properly. So Albert Einstein, I mean, he's the guy that came up with relativity, and he also helped a lot with the quantum revolution as well. So Albert Einstein, he showed that light can actually be visualized as a particle in order to explain the photoelectric effect properly. And so even though he used the particle model to show that the photoelectric effect can be explained properly, But the thing is that during that time, scientists were still very reluctant to accept that light is a form of particle, because it's such a weird idea that being light and a particle at the same time. And that is about 20 years later. There is something called the Compton effect, where you have a stationary electron and then you shine light onto it. And so what happens is the light, they start to scatter. And according to the Compton effect, it can only be predicted properly if we actually treat light as a particle, and we treat the interaction between a light and a particle as if, you know, two kind of two like balls hitting together, like two particles colliding. So it was a Compton that really like convinced everyone that light is actually a form of a particle as well as a wave. But for VC, for year 12, the only two things we'll be looking on is the one at the top of the timeline. So the double slit experiment and also photoelectric effects. The one that down there is just like kind of like just some extra things that are going on that I think it's a good idea to know about them. So if you're interested, feel free to kind of dig deeper into those two areas. Okay, so now let's look at the Thomas Young's double slit experiment in a little bit more detail. Okay, so what Thomas Young he discovered is this: if you take two slits and you get them very close together, and then you shine light onto the slit. Okay, so what happened is when you project the light that is passed through the slit onto a screen. Okay, so what they find is that you get like a series of bright and dark fringes. Okay, so you can see that from the picture that I've attached in the slide. So you see like a series of like bright lines and dark lines, bright lines and dark lines. Okay, so this is a really weird thing. And furthermore, if you use white light and you put it through a double slit, what happens is that you get like a very nice rainbow spectrum. Okay, so I've attached a picture over there. So at the top it's like a single color. So like maybe it could be green, could be red, could be blue, yellow. But at the bottom, if you use a white light, so what happens is the light, you know, they start to spread, and then this is what you see. So in the middle you get a nice white light, but towards the side, all the colors start to kind of like all start to spread apart. Okay, so how can we actually explain this? And this can be explained by the wave model. So according to the wave model, so what happened is when the wave hit the two slits and we pass through the two slits, they undergo diffraction. So when they undergo diffraction and then when they hit the screen, you know, they start to interfere with one another. And so when one crest meets another crest, like the peak, what happens is, you know, they construct each other. And if the crest of one, you know, meets the kind of like the lower part of the other one, they results in a destructive interference. And so I won't go into too much detail over here. They'll be studied more in a year 12 VCE Physics, just giving you like the big picture over here. Okay, so it was Maxwell that showed much later that actually, you know what, it's a form of electromagnetic wave. Okay, so now let's get into the photoelectric effect. Okay, so Thomas Young's experiment like really showed that light is a form of wave. But what about the particle effect? Okay, so this leads us to the next thing, which is the photoelectric effect. Okay, so the photoelectric effect is the effect where if you have a piece of metal, say a conductor, so when you have a piece of metal and then you shine light onto the metal, so what happens is electrons will get knocked out of the metal, and the metal starts to gain like some positive charges. Okay, so the thing is the wave model, even though it does explain that a little bit, but it doesn't really explain that that well. Okay, so the big problem with wave model is that the wave model kind of says, okay, so if you shine light onto a metal, so the electron will slowly absorb the energy until it has energy to get out of the metal. But the experimental evidence, you know, suggests that, okay, so if you shine light onto the piece of metal, electrons will get ejected like immediately. It's like you shine light onto it, electrons will get ejected out like immediately. So there is like almost no time delay between shining the light and the electrons, you know, leaving the metal. Okay, so not only that, what scientists also find is that if you use high frequency light and shine it onto the metal, you get more energetic electrons. If you shine like low frequency light, you get less energetic electrons, which according to wave model shouldn't be happening. Is because the energy of the wave shouldn't depend on the frequency. It's just like say sound, like high frequency sound and low frequency sound shouldn't. It all depends on the amplitude. That means like how intense the sound is. Frequency shouldn't be part of the picture like at all. So the photoelectric effect, like the wave model, can't really explain that very satisfactorily. So something is really wrong over here. Okay, so Einstein stepped in. Okay, so he showed that this photoelectric effect can only be explained really satisfactorily if we treat light as a stream of particles, and each particle has an energy given by this very famous equation, E is equal to hf. So the energy is equal to Planck's constant multiplied by the frequency. So Planck's constant, it has a very tiny value of 6.63 times 10 to the power minus 34. So it's a very tiny value, and depends on the frequency of light. So high frequency light, each photon has more energy, and low frequency light, each photon has less energy. And I mean, to me, this equation is probably even more groundbreaking than the equation E is equal to mc squared. I mean, actually, I prefer like this equation, E is equal to hf, because I say it's even more like groundbreaking than E is equal to mc squared, because this little equation seems very innocent. It's the one that started off the quantum revolution that ultimately led to the development of things like all the things that we have today. Right. Okay. So now I've covered photoelectric effect and the Young experiment. So photoelectric effect showed that light can be a particle, and the Thomas Young double slit experiment showed that light can be a wave. Okay. So now with these two pieces of the puzzle, we'll be able to understand like why atoms they can emit discrete wavelengths of light. Okay. So the reasoning goes like this. So with the photon model, we can now explain this properly. Okay. So as I mentioned earlier, okay, so since the electrons, they can only orbit at certain orbits, and each orbit have its own energy levels. So say the lower, the one closest to the nucleus has the least energy level, and as you get further, you get more and more energy. Okay, so you can think of electrons, being on a step. Okay, so as they're on the steps, they can either be at the first step, second step, third step, or fourth step. There is no way for the electron to be, maybe in between, the 1.5 step. It cannot be over there. Okay, so what happens is when you heat up the atoms. So what happens is the electrons, they start to get excited. So they jump up to higher levels. Okay, so when they jump up to higher levels, so this is what we call excitation. So to get excited, they jump up to a high level, and after a while, the excited electrons is, we can only get excited for, you can't get high for way too long without getting exhausted. Okay, so when they get excited, after a while, they will start to drop down back to the lower level. And when they drop down back to the lower level, they start to give off a photon. And that photon has a very nice frequency that is given by this formula, at that very specific frequency that is given by the high energy level, subtract away from the lower energy level, and then you divide it by the Planck's constant. And since every atom, they have their own unique energy levels, because different atoms have different nucleus, and that influence all the different energy levels. Okay, so this is why every atoms, when you heat them up, they give off their own unique set of wavelengths of light. Okay, so this is all explained by the photon model of light, and all the discrete energy levels. Okay, so that's pretty much all I want to cover today. Okay, so of course, like I said, I'm just barely scratching on the surface of what is really going on with more modern physics. There's so much stuff that is going on, and I can spend hours and hours and hours talking about this. So yeah, you can say I'm a really fun guy at parties. I meet someone new, and then I talk about quantum physics, for a few hours, and either they get really bored or they get really fascinated. Right, so for those of you guys who are watching this now, I just want to say I hope you learned a lot in today's lecture, and I hope you are really fascinated by quantum theory or modern physics, and go and read up a little bit more on that, and get confused, get fascinated, and so on. Okay, so for the next lecture, so it will be 2 weeks from now, I haven't really decided what topic I want to do yet. I might be doing one on math, or I might be doing one on study skills. So I'll definitely update it on the Facebook page. So for any updates, just check out my Facebook page and just like it. And if you guys have already liked it, I just want to say I love you. And so once again, thank you very much for watching. I'll see you guys in the next lecture. Take care, everyone.